I will. After I finish entanglement entropy and field theory, which I'm almost done with. So the punchline of yesterday's lecture was a proof using entanglement entropy of the C theorem, which told you that if you have an RG flow connecting one CFT to another, then the central charge of the ultraviolet CFT must be larger than the central charge of the infrared CFT. And so this is a famous theorem that goes back to the 80s, originally proven using different methods by Zamolodchikov. But it's nice to have a proof in this language of entanglement entropy. At the time that this work was done, there were no known constraints, similar constraints on RG flows in higher dimensions. And that has changed since then. So I want to start by talking about the two-dimensional case. I'm not really sure where I'm at in my numbering system, so let's just call it F. And there are various reasons why it's hard to prove an analog of the C theorem using the kinds of methods that Zamolodchikov used in two dimensions. But it was noticed, the following thing was noticed. So we should first, if we're going to use entanglement entropies to study this quantity, or to study RG flows, we should have some quantity which is an analog of C. So we should understand what the entanglement entropies look like for CFTs in two dimensions. So what you can show, so I'm going to be quite sketchy in this section. I just want to give an outline. So for CFTs, what you can show is that the entanglement entropy for a disk of radius r has the following form. Well, we've seen this before. So it has, of course, a area law divergent piece, the quote-unquote area being 2 pi r, the circumference of the circle. And then it has a constant piece. So we're talking about a CFT, so there's no correlation length here. There's no other dimensionful quantities. And it turns out there's no log. In principle, by dimensional analysis, there could have been a log, but there's no log in two dimensions. There's just a constant piece, which is called F. And F characterizes the theory. So F, it doesn't have a name like central charge. It's just called F. But it is a number that characterizes the theory, and it can be computed. So it's equal to minus the log of the partition function of the theory on a 3-sphere. Euclidean partition function, you put the theory on a round 3-sphere, it's a 2 plus 1 dimensional theory, compute its partition function, that's divergent. It has a similar structure to this, and if you pick out the finite piece, then you get the same number. So the fact that this equals this was realized by Cassini, Huerta, and Myers in 2011. And this quantity actually is one that had gathered some previous interest because it was conjectured around the same time that so that you had this conjecture that F, that under RG flow, F behaves the way C does in one dimension. And that was based on a lot of examples that were studied, using a whole bunch of different techniques from different parts of field theory. And they were all consistent with this conjecture. And then this statement was proven using this by Cassini and Huerta in 2012. And what they proved was the following thing. That if you define this quantity so this was for a CFT. Let me just try to clarify. This equation is for a CFT. Now we're interested in non-CFTs, RG flows, okay? So now S is some more complicated function of R, which presumably for very small disks is probing the ultraviolet fixed point, and for very large disks is probing the infrared fixed point. And so you compute this combination given S, and this strips off the divergent piece because the divergent piece is always R over epsilon all along the flow, okay? So that, the divergent piece is local and doesn't know or care what the full size of the disk is, except for the length, except for its circumference. So it's always R over epsilon. So when you take this combination, you always strip off at any scale the divergent piece, okay? And you're left with some finite function of R, and what they showed was that the derivative is negative. Okay, so this thing, this is finite and equals F on fixed points. And then they proved, so by the way, this, well, this idea of using this function was due to Liu and Meze. And then given this idea, Cassini and Huerta proved that F prime of R is negative, which implies the statement we wanted. There's some, I've got some sign messed up. No, that's right. I don't think I have a sign messed up. This F theorem is the only known constraint on RG flows for two-dimensional field theories. And they proved this using strong subadditivity and relativity. So it's a more complicated version of the proof I gave yesterday in one dimension. It's actually fairly complicated and involved, so I'm not going to try to reproduce it. But it has the same ingredients. We don't have any constraints on RG flows using entanglement entropy in higher dimensions. There is a proof of a closely analogous theorem for D equals 3, which is called the A theorem, which is proven in a totally different way. And that's all we know. We don't know anything about 4-dimensional or higher RG flows. Okay, any questions about that? Yeah.
What's the status of conjecture about this? Is it thought that in higher dimensions there is an analogous theorem that's just harder to prove, or?
There's evidence for a C theorem in 5 dimensions. My counting is off because in high energy theory we add 1 for time, but I'll try to stick to this. So in D equals 5, there's strong evidence for an analogous theorem not coming from entanglement entropy. There's virtually no information from entanglement entropy on higher dimensions in terms of examples or conjectures. or even ideas for proofs. The basic reason for that is that in order to strip off the divergences in higher dimensions, you need to take more derivatives. And the quantities you construct in that way, you can show are not monotonic. And furthermore, there's no reason they should be monotonic because, as I emphasized yesterday, strong subadditivity is essentially a constraint on a second derivative. Here, you notice here and also yesterday, we were taking a second derivative of S. If I'm taking higher derivatives of S, I would need some constraint, which is not from strong subadditivity. Well, that's what I was saying, that in 5, D equals 5, there's a conjecture and strong evidence for it, but not from entanglement entropy. Yeah. And 4, I don't even think there's a statement. I don't even know of a conjecture. Yeah.
But 3 plus 1, the A here has similar content.
Yeah. It's similar to the Zamolodchikov C theorem. Yeah. Not based on entanglement, based on studying scattering amplitudes actually, and in unitarity of scattering amplitudes. So it's kind of a weird situation. A lot of this, the differences between dimensions are due to the different structures of the anomalies. That's essentially where this is coming from. And the fact that we don't have, the fact that we only have an entanglement-based proof for 2 dimensions can be traced to the fact that there are no anomalies in even spatial dimensions. And so there's kind of nothing else to work with. So entanglement kind of is a gift because it's like this totally different tool we have. This is also why there are no logs. Okay, the last thing I want to talk about is I want to go back to D equals 1 CFT and want to talk about 2 intervals on line, and let's say in the ground state. So I have A, I guess I could use color, couldn't I? That wouldn't kill me. So A and B. Okay, and here what we might be interested in is the mutual information for reasons that I explained at the beginning. And it turns out that in CFTs it's much harder to compute this than for one interval, much harder. And it depends on the full, on the other hand, it's much richer, whereas the entropy of a single interval depends only on the central charge. The entropy of multiple intervals depends on all the details of the theory. And let me give you an example of what this looks like. And actually, yeah, so first I'll just write it out. So massless Dirac fermion, this was done by Cassini, Fosco, and Huerta. 05. We'll just stare at this for a second. So I'll call this endpoints A1 and A2, B1 and B2. And this is what it looks like. 1/3 log of the following cross ratio. Now, I want to say a bunch of things about this formula. The first thing I want to say about it is that this is the only theory where the mutual information has ever been computed exactly. we don't know the mutual information in any number of dimensions for any theory except for this one, in terms of exact results. We have approximate results for many, many, many other theories, but as far as exact results are concerned, this is all there is. Which points to the fact that entanglement entropies, as useful and fascinating as they are incredibly difficult to calculate in practice, which kind of often limits their usefulness. Now let's look at this, and even though that's true, the qualitative features of it actually hold for any CFT. So here's a bunch of qualitative features. First of all, it's finite. The epsilons are gone because the epsilons are due to the divergences which are located at the endpoints, and those cancel out of this. That wouldn't be true if my two intervals touched each other. Then I would still have a divergence. It's not zero. Well, it's not zero. If it was zero, that would mean there's no correlations, which would mean that all of the connected two-point functions vanish, which is not true. So as long as your CFT is non-trivial, I mean, my previous statement about it not having been computed in any other theory excludes topological theories where it has been computed because it's zero. But in a CFT, in a non-trivial CFT, it's not zero, can't be zero. Because it doesn't involve the epsilons are the only things that break the conformal invariance of the theory. The epsilons are gone, so this thing must be conformally invariant, and you can check that this is a conformally invariant cross ratio. And furthermore, it's analytic. Everything in CFT is usually analytic as a function of cross ratios and so on. If you take the limit that they touch each other, you expect a divergence, and you can check that this thing, if I take B1 minus A2 to 0, then I pick up a divergence. In the other limit, where they get very far apart, it goes to 0. Let's say they get far apart, but I fix the sizes of the two intervals, and I just take it to infinity. And it does so, if you work it out, it does it like this. This power, B1 minus A2 to the 2h, where h is the dimension of the lightest spinless operator. So in this case, h is 1 for the Dirac fermion, so it's b1 minus a2 squared. You can check how that goes to 0. It looks like this. I should have sketched this before. This is the separation b1 minus a2, and it goes like this. And it decreases, let me put it this way. By strong subadditivity, we know that if I extend B a little bit, it has to increase the mutual information. So if I leave all the endpoints fixed except for I make B2 a little bit bigger, it has to increase the mutual information. And you can check that that's true. Because this depends only on the cross ratio, that implies conversely that if I hold the sizes fixed and increase the separation, the mutual information has to go down. So increases with increased sizes of intervals, which implies decreases with separation. And that's what we see. So you can compute this quantity numerically using various methods in all kinds of other CFTs. And there's a small industry doing that. But yeah, any questions about that? And in higher dimensions, you can also consider mutual informations, and there's a similar story. Okay. The other thing I want to say before moving on to the next topic is that, as I said at the beginning, I think I've only covered like maybe half of 1% of the applications of entanglement entropy in field theory. And so, you know, I couldn't even probably think of all of them. But, you know, one topic I haven't touched on at all is time dependence. So if you have time dependent states, then you can ask, what is the time dependence of the entanglement entropy? And this gives you a lot of information about the dynamics of your theory. There's all kinds of things in condensed matter physics and statistical physics, like many-body localization. You can use entanglement entropies to detect many-body localization, and all kinds of other stuff. But I'm not going to go into that because I want to move on to topic 3. But before I do that, are there any questions about any of the stuff that I've covered so far? Oh, what? The mutual information, I mean, numerically, yeah. Yeah. Mm-hmm. Yeah.
So in 2 dimensions, I just have some scheme where I grow my 2 domains and separation does that mutual information. In other words, there are all these tricks basically to take off the divergences, and this is hard to calculate.
Right, so there's an interesting question about, you know, here I use the disk. So this is, despite the drawing, a round disk. But of course, I could take any shape, or even a disconnected shape, and compute this for it, and it would strip off the divergences. And it turns, of course, at the fixed points, you won't have such a nice thing, but but maybe you get something, and maybe you get a whole collection of F theorems, one for every shape. This is not very well understood, whether you do get another F theorem for every shape, but I would say the most likely situation is that, except for the disk, they're not monotonic. The disk is special. The round disk is the only one that's monotonic. Now, it may be that for others, it's larger at the UV fixed point than at the IR fixed point, but it would be hard to prove that if you don't know that along the way it's monotonic. But this is actually an open problem. Yeah. I don't think any counterexamples like that are known. It's a good question. Okay. Any other questions? Okay. So I'm on to my next topic. Which is holography. And I guess I'll start over there. So Well, I think I've emphasized that it's very hard to compute entanglement entropies in field theories. And what I'm going to talk about next is an exception, which is actually kind of surprising. So what I'm going to tell you is that in certain theories where you would have thought that it's extra hard, it's actually extra easy. And those are ones that might seem at first sight to be the most complicated possible theories, where you have a large number of fields, and they're very strongly interacting with each other. But it turns out that there's a thermodynamic limit where it simplifies. And that has a very deep and beautiful connection to geometry and general relativity. Okay? So I'm going to start by giving an introduction to holography. And I'm only going to say the bare minimum that I need to say to talk about entanglement entropies, so holographic dualities. Okay, so we're going to consider some QFT in d dimensions with n interacting fields. Okay, and so for example, you could have like an SUN Yang-Mills theory, and then n would be like little n squared. Okay, and if you're lucky, depending on the structure of the theory, sometimes there's a nice thermodynamic n goes to infinity limit of the theory, where, by nice, I mean you have a collective description in terms of order 1, so if you want order n to the 0 collective fields, or collective, let me not call them fields, degrees of freedom, that are sort of behaving quote-unquote hydrodynamically, by which I mean that are governed by classical mechanics. Okay, now, usually this collective description is incredibly complicated and hard to work with. But sometimes, if you're lucky, it's actually quite simple. So another sometimes, in the limit of strong interactions, this description simplifies even more. And why and how and exactly under what circumstances this magic happens is not well understood. But we know concrete examples, and it simplifies rather dramatically to be general relativity in a larger number of dimensions coupled to some matter field, to some matter fields. Okay? So the value of D in the matter, these parameters depend on the theory you started with. on the QFT. And the GR is subject to some boundary conditions. So it's like a universe in a box. So there are some, well, let me write it over here, actually. Subject to some boundary conditions. And in particular, the simplest case, although not the only case, is if you have conformal symmetry. So if your ground state, well, let me say it this way: if your QFT is conformal, then the ground state of the GR is of this form, is a certain solution to the Einstein equation, which goes by the name ADS, in d plus 2 dimensions, times some other manifold, which is, according to my calculation, big D minus little d minus 1 dimensional. Okay, what on earth is this? This is some compact manifold. The total number of dimensions, if I did my arithmetic correctly, is big D plus 1, which is the number of space-time dimensions of my GR theory. Okay? And I'm going to forget about this part of it. This is some complication that I don't want to talk about. It's actually important for many purposes, but I'm going to ignore it. Okay? The important thing is this part. This part is space-time, which has the following metric. Oh, yeah, let me say. D plus 2, because this space-time has D plus 1 spatial dimensions plus time. That's the plus 2. Okay? And the metric looks like this. So I have D spatial x dimensions, an extra spatial dimension, and a time dimension, and I have this warp factor. R is called the ADS radius. What on earth does this thing look like? Well, let's forget time. Just the spatial dimensions are, it becomes D plus 1 dimensional hyperbolic space with a boundary. So it looks like this. Here's my z direction. And I have this warp factor, so the larger z is, the smaller these other coordinates get in their proper size. And it's just a convention that I like to draw z going downward, because that gives you the intuition of the gravitational potential pulling you down, which it does, because the gravitational potential is the coefficient of dt squared in the metric. So the Newtonian gravitational potential is kind of pulling you down. And, but there's this warp factor, which shrinks everything. This is my attempt. Okay? And it keeps going infinitely far in this direction. It's not actually cut off. This is just, it keeps going. But it stops up here at some z equals epsilon, which is our cutoff. Okay. And in some sense, this surface, so this is a boundary of ADS. And this is a d-dimensional space plus time. And you can think of it as, in some sense, as where the QFT lives. But do not imagine that I have a quantum field theory coupled to general relativity. That's a big mistake. These are two representations of the same theory. Representation one, a quantum field theory, n fields strongly interacting in this space. It is equivalent to general relativity with some matter fields living on this space, with this as a boundary condition. So you can see why it's called holographic, because we have two representations in different numbers of dimensions of the same thing, okay? So this is kind of a, the QFT is kind of a hologram of the GR. And morally speaking, okay, so the map, you might ask, okay, if I have something going on here, it represents something going on in the field theory, and what's the map? And the only thing I want to say is that the map is non-local. So a given point in this ADS is not represented by any given point on the boundary or vice versa. Okay? It's non-local in space and in time. It's very complicated. Okay? But sort of morally speaking, the UV is the stuff near the boundary, and the IR is the stuff down in the throat. Okay? You might ask why on earth we believe such a cockamamie duality, and I'm not going to really answer that, but there are a few cases where we know both sides very explicitly, and there are many more cases where we only know one side. Or we know something about the two sides. But just to give you a concrete example, basically the cases where we know both sides very explicitly are the cases where you have tons of supersymmetry, and use the power of string theory to really understand what's going on. So an example of that, the first example is in 3 dimensions when you have this SUN super Yang-Mills is equal to some supergravity theory on ADS 5, and the extra dimension that I don't want to talk about happens to be, in this case, very simple, just a 5-sphere. Most of the cases, so D in this case is 9. Most of the cases where we know the other side, it's because of string theory, and therefore it's either 9 or 10. Capital D is either 9 or 10. But that doesn't mean that those are the only cases. Those are just the only cases we kind of really understand. And let me finally say that if the theory is gapped, as opposed to being conformal, then the infrared should stop somewhere. There are no degrees of freedom at very low energies. So, and in fact, what happens is that the thing does end. So if the QFT is gapped, then the ground state has a wall where space ends. And there are various ways this can happen. This is a perfectly legitimate, consistent thing that can happen in these general relativity theories. One thing that can happen is that this extra manifold kind of shrinks to be 0 size, and so the whole thing kind of caps off smoothly. Or there's some object there, some kind of brain at which space ends. And if you're an observer living in this space, you would kind of bounce off this thing. You would know that there's a wall. and that reflects the fact that your field theory does not have arbitrarily low energy excitation. So it doesn't have a very deep IR. At some point, the degrees of freedom stop. But as long as the field theory has a UV fixed point, it'll asymptotically approach anti-de Sitter space ADS as you go to small values of z, as you go toward the boundary. On a wall, and the wall is at z, at a value of z, which is basically the correlation length of the field theory. And lots of examples like that are known of confining, for example, confining gauge theories that have holographic duals with a wall. Okay, let me make a chart in an attempt to compare and contrast these descriptions. So here we had the number of degrees of freedom, and what is that dual to? That is dual to the ADS radius expressed in Planck units. So LP is the Planck length. The Planck length, so LP to the D is G Newton H bar of the bulk. So the bulk is a gravity theory. It has a Newton's constant. It's secretly quantum mechanical, so it has an H bar, and this is presumably a very microscopic length scale and is much smaller than the ADS radius. And so in particular, the thermodynamic limit on one side, which is n goes to infinity, is the classical limit on the other side of L Planck goes to 0. So we have, in terms of modes of the theory, we have the collective modes, or we have the individual modes of the original fields. And so for example, if we had a Yang-Mills theory, we would have the gluon fields, of which there's big N, and then we have like the glue ball, or the confined fields, the collective modes, of which there's order 1. And so the collective modes, and this is a description only of the collective modes, okay? The excitations of the original gluon fields are not well described within this GR system. Those are very, very high energy modes. So the collective modes are, basically all the excitations of this GR, which are gravitational waves, and you have different kinds of matter in here, and they have waves and so on. Okay. When you study a quantity, you can do an expansion in 1 over n, and so you can study the fluctuations away from your thermodynamic limit, and those are dual to quantum fluctuations. So if you want to understand those, then you have to do quantum mechanics in the bulk, which you would do generally using string theory or something. So you would have to do, in other words, you have to do quantum gravity in the bulk. And that's fine as long as you're doing just, some perturbative calculation. You have the tools to do that generally. It might not be easy, but in principle, we know how to do it. And now, if you heat this thing up to a high enough temperature, you may deconfine these elementary excitations. Okay, so if you heat it up a little bit, then you'll just get, like if you have a mass gap, okay, and you just heat it up a little bit below the mass, then you won't, what you'll just get is a few kind of glue balls running around, okay? And those are dual to just a gas of gravitational waves and stuff in the bulk. But if you heat it up enough, you will deconfine the theory and get a plasma of the elementary excitations. And how is that described? Well, that's described by having a black hole in the bulk. Okay? So a deconfined phase is described by having a black hole. And so then you actually get a horizon in the bulk at some value of z. So this, you know, I said before, the wall is kind of innocuous. If you're an observer living in the bulk, you'll bounce off the wall, but you will not bounce off that horizon. You'll fall into the black hole. Okay? Falling into the black hole is being thermalized. Okay? You fall into the black hole, you disappear. Okay? And that's the dissipation of being in this plasma. Okay? You just melted into the plasma. Okay? And the entropy in this phase, because there's order n elementary fields, the entropy is proportional to n. And if we calculate the entropy on this side, we do it using the Bekenstein-Hawking formula. Bekenstein-Hawking tell us that the entropy is the area of the horizon over 4 L Planck to the d. The area of the horizon is something in units of r. So this is like r over L Planck. The horizon is d-dimensional, because remember these directions are d-dimensional, so this is r to the d over L Planck to the d, which is n. So that's good. Okay, so this is one way to tell that this black hole must represent a deconfined state. It's a state in which the entropy, and this will be a phase transition, the entropy jumps from being of order 1 to being of order n. Okay, so it jumps from being a state where you just have collective modes at low temperature to one where you've deconfined the elementary modes. Okay? Okay, that's holography. There's obviously like a ton of stuff you can compute using these dualities that you can't compute in the field theory itself. The field theory, again, is some strongly coupled large N field theory, hopeless to compute things pretty much. And there's, you know, whole courses you could give about what you can compute using these. People compute things even for, you know, quantum chromodynamics and compared to experiment, or for many bodies, strongly interacting many body systems in condensed matter physics and compared to experiments and so on. There's a lot of mileage you can get out of these. But what I want to talk about is entanglement entropy, but first questions. Yes?
Doesn't the area of the horizon depend on the where it happens?
Yeah, that's right. So this is, I'm just giving you the dependence. So that's, you know, of course on this side it depends on the temperature. It's n times some function of the temperature. And the z where it happens depends on the temperature. Not I mean, actually, so the details depend on the particular theory, but basically the lower the temperature, the lower your horizon is. And, you know, in the limit of high temperature, the horizon starts to approach the boundary. And then what happens is the whole system becomes kind of d-dimensional. You lose this extra dimension, and that's the limit where hydrodynamics is a good description. Hydrodynamics in the original, you know, d dimensions is a good description. So at sufficiently high temperature, the whole thing, you know, you can basically forget about holography and use hydrodynamics. Here I just wanted to get the n dependence, but you're absolutely right. Any other questions? So the point I want to make now is that aside from all the other amazing, wonderful things that holography has given us, it allows us to compute entanglement entropies very simply. And conceptually, what it does is it geometrizes the whole story about entanglement entropy in a very beautiful way. And this whole story is due to two people named Ryu and Tarayangi. Who said, we think that when you compute the entanglement entropy of a region in the field theory, Ben was much better at using color than me, of a region in the field theory, we think that the entropy is given by the Bekenstein-Hawking formula, except there's no black hole here. I mean, there might be a black hole down here, but what does that have to do with this region A? So when I do Bekenstein-Hawking formula, what am I supposed to put for where the horizon would go? They said what you put is the area of the minimal surface whose boundary is A. I'll call it M of A. I'm just going to move that over here. What was it? B? Area of M of A. M of A, right here. M of A is the minimal area surface in the bulk ending on the entangling surface. And there's actually another topological restriction, which is that it has to be homologous to A, which means that there's a spatial region in the bulk, which we can call R of A. So there's an R of A region such that the boundary of R of A, basically that interpolates between A and M of A. It's kind of obvious in this picture, but there are more complicated topological situations where this fixes what M of A can be. So if there's handles and stuff in your bulk, then, or holes, then M of A and R of A, then this topological restriction changes what M of A can be. So there has to be a region which interpolates between A and M of A. Okay, it's probably not evident really what this means, but I'll give an example later if there's time where you'll see the role that it plays. This is the leading order term. So this area is going to go like R to the D. It's an area of a surface. So because it's codimension 1, the bulk is D plus 1 dimensional. It's a D-dimensional surface in a geometry whose overall scale is R. So it's something times R to the D. So this thing is R to the D over L Planck to the D. So this thing is order N, which is what you expect for the entropy. And there's corrections which are due to basically, this is some, from a bulk point of view, quantum correction. So it's funny because what we're saying is that the entanglement entropy, which by definition is a quantum thing, from the field theory point of view, is given by something totally classical, or it's given at leading order by something totally classical in the bulk. You just find your minimal surface in this fixed geometry, which is relatively easy to do, and that gives you the leading piece in a 1 over n expansion. And then this stuff is harder to compute. But actually, we know quite a bit about this stuff also, but I'm not going to go into that now. I mean, the short version is that the first correction is due to entanglement in the bulk between this R of A and the complement of R of A. So it's due to bulk entanglement. That gives you the statistical fluctuation contribution to the boundary entanglement. So now we just have to talk about minimal surfaces, and what I want to show is that the whole story we've been telling so far is just gotten geometrized. Okay? So the first thing I need to show is that you reproduce the area law divergence for this to be plausible. Okay, you can ask, by the way, how we know this is true. And we know it's true basically for three reasons. First, in the few cases and examples where you can compute this exactly from first principles, they agree. The second is that this obeys all kinds of non-trivial properties of entanglement entropy, like strong subadditivity. And the third is that there's a derivation of it from first principles, which is a little bit cheesy. I mean, as a derivation, it's a little bit cheesy. It's kind of, you put in, it has like leaps in it. It's not like really rigorous, but that's okay. So I would say we have like enough evidence that it's true that nobody really doubts it at this point. But there's nothing in this whole holography story that we understand rigorously anyway, so it's not that different from the rest. Okay, the area law divergence is easy to see. We just want to zoom in. So one thing I didn't say is that, so the metric you see is blowing up near the boundary. I erased my metric, I shouldn't have done that. But you have this 1 over z squared in the metric. That means that it's very expensive for this surface to wiggle in this direction as it gets close to the boundary. That means that as I drew it, it meets the boundary orthogonally. Okay? So the curvature makes it want to go into the bulk because down here the metric is smaller, so it's being pulled down by the desire to have the smallest area possible. And then up near the boundary it does the minimum, which is to meet the boundary orthogonally. So near the boundary, so M of A meets the boundary orthogonally. And if we just zoom in, and let me call this x1. These are my other x directions, well, x2, xd, and then z. It just comes down orthogonally. And we're only interested in what it looks like in here. And when you compute the area, the area is the integral d, we're just integrating in these directions, so it's d minus 1x of the square root of the determinant of the induced metric. So that's the metric on the surface. Well, the metric on the surface is just, so induced metric is just has 1 over z squared, sorry, r squared over z squared, dz squared plus dx2 squared to dxd squared. So that's the metric on this d-dimensional surface. And so root det h, if I take the determinant of this, is just r over z to the d. And sorry, this is also integral dz. Sorry, let me write it here. dz, but only starting at epsilon, we have our cutoff. Okay? Well, this looks, so this integral is just my old friend sigma, which is the area of dA. So I get sigma integral dz r over z to the d, starting at epsilon, my cutoff, which is exactly the kind of thing we had before when we were estimating the, when we first derived the area law. So you get sigma r to the d over epsilon to the, yes, to the D, whoops, yeah. And therefore, S of A is R over L Planck to the D, that's my N, sigma over epsilon to the D minus 1. So this is my good old area law divergence. And it basically, this surface is kind of telling you how much entanglement there is between degrees of freedom. And the deeper part of the surface is the entanglement between IR degrees of freedom, and the part closer to the boundary is the entanglement between UV degrees of freedom. And by the time you're done integrating up to epsilon, you end up with this same power of epsilon we had before. So you reproduce that very nicely. Another example is a CFT in D equals 1. And this is what we're going to do in the tutorial, so I'm not going to do it now. But the minimal surface looks something, you'll derive the actual form of the minimal surface and its area, but you reproduce this formula. So that's going to be for the tutorial. If it's gapped, then something interesting happens. So now I have so this is Z equals epsilon. This is Z equals some Xi. And if A is small compared to Xi, if L is small compared to Xi, then my minimal surface doesn't even know about this wall. But if it's large, then something interesting can happen, which is that it can switch to a different choice of minimal surface. In fact, it has to, where the minimal surface just goes straight down to the wall and ends on the wall. And after that, it doesn't depend on the size anymore. So it looks like this. There's a phase transition in S of A. And remember, we talked about gapped systems before. And what we argued is that in gapped systems, it saturates. Here we see that it's not just saturating, but there's a sharp phase transition at some L of order Xi. In the tutorial, we're going to see exactly where this phase transition happens in a simple, crude model. Of course, it depends on the details of the geometry. Okay? But we're reproducing this feature, which basically is saying that at some point, there aren't any more, there's no more entanglement because of the stuff in here. The entanglement is due to stuff in here being entangled with stuff out here, but the stuff in here, in some sense, is not contributing anymore. If I make this bigger and bigger, it doesn't change the entanglement entropy, which means the stuff in here was not entangled with the stuff outside. Only like the stuff in some neighborhood was entangled, which is what we saw in the field theory. But now this is reflected by adding this extra dimension in this funny competing minimal surfaces business. Now, at finite temperature, and you can do this in higher dimensions. So at finite temperature, well, now we have a black hole to contend with. So there's a horizon, and it's very different because the horizon itself carries entropy. you don't get a phase transition. If A is small compared to the temperature, so this thing is like 1 over the temperature. If L is small, then again, it doesn't know, compared to the thermal length scale, it doesn't know that it's at finite temperature, and you get whatever you would have gotten before. But what happens if I make it larger? And when you study geometry, the minimal surface, what it does is it skirts the horizon, and you have a contribution which is linear in the size. So this is your volume law thermal contribution. So your S of A looks like this. It doesn't saturate, instead it picks up a linear piece. And where does that come from here? It comes from the fact that the horizon has some entropy density given by the Bekenstein-Hawking formula, and the minimal surface is now sensitive to that because it's skirting the horizon, and it has a part of its surface area is given by a part of the horizon surface area. Same entropy density because it's all Bekenstein-Hawking formula. It's all 1 over 4 L Planck to the D is always the entropy density. And so you pick up this volume law contribution. It's the same deal in higher dimensions. I'm just drawing it in D equals 1. Okay? So all of the qualitative features we saw are well represented here in a rather nice way. And let me also point out something funny that happens at finite temperature, which is the following thing. If you're in a pure state, then any region has the same entropy as its complement. And you can see that because, well, like here or whatever, here, if I look at the complement, and I look for the minimal surface, well, guess what? It's the same. Because the boundaries are the same, right? The boundary of A is the same as the boundary of A bar. So you're solving the same minimization problem subject to the same boundary conditions, you get the same answer. Okay? But you know that if you're in a mixed state, it's not true that A and A complement have to have the same entropy. It can happen, but usually it won't. How do you see that here? Well, isn't it still true that A and A complement have the same boundary? And therefore, isn't it still true that M of A equals M of A bar? Well, the first part was true, but I have a talent for erasing the thing that I just need at that moment. What I just need is this homology condition, which was written out in a long sentence. But the homology condition says that you need a region that interpolates between A and M of A. So for example, here, there's my region. But if I try to make a region that interpolates between A bar and this curve, the boundary of that is not M of A because the boundary has another part, which is this. And in fact, the minimal surface, which is homologous to A bar, looks like this. And here's my interpolating region. And they're not the same, and they don't have the same area. And so S of A is not equal to S of A bar. So this is a very simple example of how properties from quantum information theory get translated into geometry. And now I want to give you a more non-trivial example which is this subadditivity and strong subadditivity. So let's talk about subadditivity. Subadditivity tells you that S of AB is less than or equal to S of A plus S of B. And this is very easy to prove in this context. Let's draw it. It's almost obvious. Now, if I take the union, I'm going to look for some surface which ends on A union B. This is a surface that ends on A union B, but it's certainly not minimal. The minimal one will probably look like this. But since this was an option, you certainly have the area of M of AB cannot be larger than the area of M of A plus the area of M of B. And that's subadditivity. More interesting is strong subadditivity, which requires a similar argument, but just a little souped up. In fact, let me just do it on the same. Strong subadditivity says this. So I need a C. And I need, the left-hand side looks like this. Here's my M of AB. Here's my M of BC. The left-hand side is the total area of the sum of these two. I'm interested in the sum of these two. Well, let me do the following thing. Without changing the area, let me just reconnect these. The sum of these two is the same as the left-hand side. I haven't changed it. I just reconnected. This guy now is ending on B. This one is ending on ABC. So this is a candidate for the minimal surface. It doesn't look minimal. It's probably not. But it certainly, by definition, bounds the minimal surface area above. And this bounds the minimal surface area for ABC above. Done. Okay? So you see that this Ryu Tarayangi formula very simply and straightforwardly obeys these very non-trivial properties from quantum information theory. So it's like general relativity has read the quantum information theory textbook and has incorporated some pretty sophisticated quantum information theory into it. Okay? And in fact, there's more than this. You can show that all known properties, general properties, so if you look at all the theorems that have been proven, about entanglement entropies in general quantum systems are obeyed by, there's actually an infinite list of inequalities. It's very powerful. Now, well, this was kind of a, let's see. This was my G. E, G, yeah. I'm pretty good with the alphabet. Okay. Now, let's do this famous case of the mutual information, which we couldn't do, remember, except for the Dirac fermion. And I'm going to do it. Actually, you're going to do it in the tutorial. And you might say, well, isn't that another example? But it doesn't count because we're not computing it exactly. We're only computing the leading large N contribution, remember. It's not an exact calculation, okay? But this is what we're after. I don't know what color scheme I used before. And I want to point out that something very interesting happens, which is not dissimilar to this case, where we had competing minimal surfaces. We want to compute this, which requires us, so we already know this. We already know this and this. We need to compute this. So we need to find a minimal surface which ends on the boundary of A union B. The boundary of A union B is now 4 points. And if you include this topological constraint, there are two possibilities. One is this. So this I'll call M1 of AB. I need another color. Another possibility, what's another possibility? Somebody tell me. Yeah, so you can just have the A1. So this is M2 of AB, and M2 is the union. So you have to figure out which is smaller. And that depends, as Jonathan was saying, if they're far apart, then you can imagine that M2 is smaller. And in that case, it's very interesting because that would, the area of M2 is, of course, the area of M of A plus the area of M of B. And that implies that the mutual information vanishes. Now, you might object, because I told you before, for any CFT, the mutual information does not strictly vanish. But remember, we haven't computed it exactly. It's just the order n part vanishes, and it's order n to the 0. You can compute this and find that it's non-zero. The correction is non-zero. But when they're close, then, then this thing is order n. So let me draw it. So as a function of the separation, the mutual information in units of n goes to infinity as the separation is 0, and it drops to 0 at some value of the separation that you'll compute in the tutorial. And of course, this logic applies in any dimension. You know, if you have two regions and you separate them, there'll be a phase transition at which the mutual information drops to 0. So this means the dynamics are very different on one side from the other. So when they're close together, the elementary fields, you have enough entanglement of the elementary fields that they are actually correlated. That's an order n mutual information. When they're far apart, you just have whatever long distance correlation of the collective modes. And that's order n to the 0. Okay? So again, there's a lot of stuff that's reproduced by this formula, and then there's some new stuff. And this is an example of a new thing, this phase transition. So phase transitions in general are a new phenomenon that you get from this, which is not too surprising because we're in a thermodynamic limit, so you're going to get phase transitions. Another thing which is new, and this is my last thing, is you can prove this inequality you can prove that the mutual information is superadditive in each of its arguments. And I'm not going to go through the proof. It's similar to that, but more complicated. But let me give you an example to convince you at least that this can happen. Imagine that you have A, B, and C arranged in this particular way. And I've already hopefully convinced you that the mutual information between A and BC, if they're close enough together, is non-zero. But I could arrange it because B is smaller than BC, so that the mutual information between A and B is 0. In other words, we're down here. And the mutual information between A and C is 0, so these are both 0, but this is not 0. Now, that is not a proof that this is always true. That's just an example of where that's true. Okay. But it turns out this is always true in any holographic theory. It's a consequence of Ryu Tarayangi. And as an exercise, you should find a counterexample, find a quantum state that violates this. So my point is that this is special to holographic theories. It is not, in general, true of quantum systems or even classical systems. You could even find a classical state. It's actually very easy to do. So I challenge you to find classical or quantum, up to you, that violates this inequality. It's not hard. Don't look for something complicated. Look for something very simple. But that state, whatever you've come up with, will not be realizable holographically. Okay? So holographic systems are constrained in some way. There's actually many more inequalities like this that are known, that are more complicated, but sort of the meaning of them or the origin or what it tells us about holographic systems is not really very well understood. All right, so that means that they're plus new properties, or not, let me say, plus special properties. So again, I've just scratched the surface. I mean, I hope I've convinced you that this holography business translates what we knew about entanglement entries and field theories into this very beautiful and very simple geometric language. There's a ton more stuff you can do. Of course, you can calculate it in all kinds of different backgrounds, and there are many papers doing that. One thing I didn't talk about at all is time dependence. So you can calculate these in time-dependent backgrounds, and there's lots of fascinating things you can do there. There's a philosophy that you should actually take the Ryu Tarayangi formula as being fundamental and try to reconstruct holography from it, as opposed to deriving it from holography. And that would be saying that entanglement entropy is like fundamental, and that somehow in quantum gravity, you start with some quantum system with a large number of degrees of freedom and some intricate entanglement structure, and that entanglement structure gives rise to a geometry. And one example of work in this direction is that, it's kind of baby steps, but it's very interesting, is that you can use properties of entropy. So here I prove that Ryu Tarayangi obeys properties of entropy, but you can use other properties of entropy, specifically the positivity of relative entropy, to derive, assuming Ryu Tarayangi formula, the linearized Einstein equation in the bulk. Okay? So and it goes both ways. Well, okay, the other way is a little more complicated, so let me just write it in this way. So you can derive, at least in some limited context, the Einstein equation from information theory. Okay? So now there's a certain idea out there, lore, that somehow, entanglement is the fundamental thing out of which geometry emerges in quantum gravity. This has not really been fleshed out, but it's certainly an intriguing idea. Okay? And amazingly, I managed to finish early, so whatever questions you have, we can hopefully have time to address them. Not of the surface, so in a situation like this, so as I said very briefly before, I don't know which picture to point to, let me draw a new one. You have your R of A, and the bulk is described by classical general relativity at leading order, but of course, if you want to understand the order n to the 0 stuff, you need to include quantum corrections in the bulk. So really it's described by a quantum field theory, by quantum gravity, but if we're just doing semi-classical, so we're just doing an order-by-order perturbative thing, you can think of it as quantum fields propagating on some background, where those quantum fields include the fluctuations of the gravitational field itself, but that is still a quantum field on a fixed background. Because it's a quantum field, it is entangled, and it's entangled across the minimal surface. And its entanglement entropy is that correction. So for example, in this case, if we're far apart, if we're in this regime, the mutual information, this mutual information, is the mutual information between R of A and R of B of those quantum fields. So those are the, from a boundary point of view, those are the fluctuations of kind of the collective modes. So it's not geometrical, you now are actually back to doing quantum mechanics, but now in the bulk. Well, the point is the relation between the linearized curvature and the stress tensor. So it's the fact that what you get it's the fact that what you get on the right-hand side is the physical energy of the fields. So in your statement, there are a lot of assumptions built in, like general covariance, for example. If you demand that the theory be generally covariant, then yes, the Einstein equation is kind of inevitable. And you don't worry too much about what's on the right-hand side. You just say, whatever's on the right-hand side, I'll define that to be the stress tensor. Then in some sense, it's inevitable. But here in this derivation, they haven't assumed general covariance. They just said, okay, you have a background plus a small correction. The background is anti-de Sitter space, but now we have some matter. So there'll be a correction to the geometry, and we compare the correction to the geometry to the stress tensor, and you find that this implies the same thing that the Einstein equation implies. So, I didn't say it, but the fact that the bulk is described by the Einstein equation, and in particular the fact that the bulk has general covariance, is incredibly mysterious from a boundary point of view, because that is a symmetry. Of course it's a gauge symmetry, but it's a symmetry that has no counterpart on the boundary. And let's go to lunch.